So today we are talking about calculations involving strong acids and strong bases only. And I make a great point of emphasizing that these are strong acid calculations, not weak acid calculations. Weak acids get their own week. Okay, all next week we're talking about weak acids. So they get their full week devoted to them. Whereas strong acids only get 1 day devoted to them. So they, by comparison, are a lot less work, right? So let's first talk about the self-ionization of water, otherwise known as the autoionization of water. This is something that happens when water gives a proton to itself. Because remember we said water can act like an acid or a base, right? It can donate an H+, or it can accept an H+. Water can donate to itself. It can act as an acid and a base with itself, right? And so here's the reaction that produces that, right? This water gives an H+ to this water, right? So this water is acting as the acid, this water is acting as the base, right? Donor, acceptor. So you get OH- and H3O+. This is an equilibrium reaction. So here's the equation, 2H2O, right? Because you have to have two of them, one to donate, one to accept. So 2H2O is in equilibrium with H3O+ plus OH-. Now when we write KW, the W stands for water, right? So this is an equilibrium expression. And this is occurring in my bottle of water here, right? I mean, it's occurring all the time. Now why is H2O omitted from the KW expression? It's a liquid, right? It's a liquid. So we're not including it at all, right? So KW is equal to the concentration of hydronium times the concentration of hydroxide. So this is the dissociation constant for water. Will this be the same at every temperature? If I increase the temperature, what will happen to KW? Will it be the same or will it be different? It'll be different, right? KW, just like any other equilibrium constant, is going to be temperature dependent. So at 25 degrees Celsius, you don't need to write this down, as long as you know that at differing temperatures, right, KW is going to be different, right? So as you change temperature, you're going to get a different KW. So we need to talk about, we're going to use KW as a way to define if a solution is acidic or basic, right? If a solution is an acid or a base. So if there's equal amounts, we say that the solution is neutral. If hydronium is greater than hydroxide, we say it's acidic. And if hydronium is less than hydroxide, we say that it is basic. And this table is on the course website. Okay, this exact table, it's in the notes that are posted online, so you don't need to write every word of it down. At 25 degrees Celsius, which we consider room temperature, KW is equal to 1 times 10 to the negative 14th. The value of KW at room temperature is 1 times 10 to the negative 14th. So is the reaction mostly, if we're looking at the reaction, if the temperature, at room temperature, it's 1 times 10 to the negative 14th, is that reactive favored or product favored? K equals 1 times 10 to the negative 14th. Do I need to be concerned that I am drinking in a whole bunch of hydronium and hydroxide? No, I'm at room temperature right now. What am I drinking? Mostly this, right? Very, very, very little of this. So I'm okay, right? I'm not going to poison myself drinking my water here at room temperature, right? Because the equilibrium lies far over here. 10 to the negative 14th is a very small number, right? So we are defining acids, acidic solution, basic solution, based on the ratio, right? If hydronium is greater than hydroxide versus if hydronium is less than hydroxide. And then if they are equal, we're calling it neutral. Again, this entire table is posted online on the notes. So here's an example. Calculate the concentration of hydronium in a solution at 25 degrees Celsius if the hydroxide ion concentration is this, 1 times 10 to the negative 5th molar. Okay, well, I know that at 25 degrees Celsius, KW is 1 times 10 to the negative 14th, right? So I just plug the KW value in. This is what I'm looking for, and then plug in my other value, right? So how do I get H3O plus by itself? Just divide both sides by 1 times 10 to the negative 5th. So I get 1 times 10 to the negative 9th. Now I just ask myself, okay, which is present in the greater quantity, the hydronium or the hydroxide? Well, this one's 10 to the negative 9th, this one's 10 to the negative 5th, right? So I would consider this solution basic. Now this is great, right? This is a great way to calculate and determine if a solution is acidic or basic, and you can do this in the lab. But, I mean, it's kind of a pain to measure out molarities that small, figure out their concentrations. So we're going to come up with another way that we can classify solutions as acidic or basic, and you're probably familiar with it. You know it as pH. But let's just try this one just for fun, Calculate OH minus if H2o plus is 10 molar. I mean, before you even pick up your calculator, are you going to expect the hydroxide ion to be very big if it's 10 molar H2o plus? No, it's going to be an obscenely small number. So I'll give you a second to try this one just to confirm it to yourself. So with a concentration of 10 molar, I mean, that's incredibly strong, right? That's very, very concentrated. I wouldn't even need to calculate the hydroxide ion concentration to know that this is going to be what? Acidic or basic? Way acidic, right? That's very acidic, right? Because when I calculate that, I get 1 times 10 to the negative 15th. Good grief, that's really small, right? This is very, very, very acidic. So this is leading us up to pH, but it's a good place to start because if you understand this, you'll understand where pH comes from. Now, just a reminder that Kw is temperature dependent, okay? And it's only 1 times 10 to the negative 14th at 25 degrees Celsius. So if you're doing your reaction in boiling water, or if you're doing your reaction in an ice bath, right, Kw would be different. So just keep that in mind. We carry out all our reactions here in temperature, so we're not worried too much about it. But let me ask you this question. Here's what happens to Kw at 60 degrees Celsius. At 60 degrees Celsius, K is 10 to the negative 13th. K is 10 to the negative 13th. So just some practice on figuring out reactions, exothermic versus endothermic, based on K values. Would we predict this reaction to be exothermic or endothermic? What do you think? What happened to K when we increased the temperature? It went up, right? 10 to the negative 13th is bigger than 10 to the negative 14th. So if K went up, what does that mean? It means what? Well, the concentration of products increased, right? So yes, endothermic. Good. There's a question like this on the exam. It was about 50-50. We'll talk about the exam after we're done with today's material. But there was a question about, I don't think I gave you Ks, I gave you something else. I think I gave you observational data. But anyway, what I was trying to get you to think about was because K went up, that means that the concentration of the products must have gone up, right? Which means that it must have been endothermic, heat must have been a reactant. All right, so the pH scale, this is something that I think everybody's heard of before, yes? You've heard of the pH scale, it's probably something you've seen in the past. It ranges from 0 to 14, okay, and it's based on the concentration of hydronium. It's based on the concentration of H2o plus. So we're measuring acidity here. So 0 to 7, we're considering acidic. 7, we're considering neutral. So technically, you can make this 0 to 6.9999999, right? 7 is neutral, and then some value greater than 7.0 would be what we start calling it basic. But again, it depends on your Sig Figs, right? How many Sig Figs you're allowed to keep would also help determine those cutoff points. So on your calculator, if you have your calculator handy, just want to tell you something. Some calculators freak out if you enter that negative, and some calculators don't care. And some calculators require you to put a negative in parentheses. Okay, so let's pretend my concentration of H2o plus is, I don't know, 0.01. Okay, so if I'm taking a log of 0.01, On my calculator, I'd say 0.01 log. It gives me a negative number, okay? A negative of a negative is a positive. Because in my calculator, if I say negative log, it says error. It doesn't like that. So if your calculator tells you error when you enter a negative, you can either put parentheses around it or just know to change the sign, okay? Just FYI on calculator issues. Now, because this log is here, this means that this is a logarithmic scale, right? The pH scale is logarithmic. Log base 10, right? So that means that if I go up 1 unit in pH, if I go up from 0 pH to 1, I've got a 10-fold increase, right? The acidity's gone up 10 times because this is log base 10. If I go from pH of 1 to pH of 2, the acidity has changed 10-fold, right? If I go from 2 to 3, that's a 10-fold increase, right? Because this is 1, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. See what happens here? This is a logarithmic scale. So that means that anytime you change pH unit, going from 3 to 4, that would be 10 times increase, okay? Now let's talk about sig figs and logarithms. We haven't dealt with sig figs and logarithms, so let's talk about that. So the number of sig figs in your original concentration is the number of decimal places you keep in your pH. So here's an example. If I have H2o plus of 1 times 10 to the negative 9th moles per liter, this value's got 2 sig figs, right? That translates into 2 decimal places in my final answer, okay? So you'd enter it in your calculator just like any other number and take its log, and then you round based on the sig figs here. And then vice versa. If I had 2 decimal places in my pH, when I convert it back to a concentration, that would be 2 total sig figs, okay? So vice versa. 2 sig figs here means 2 decimal places here. 2 decimal places here translates into 2 sig figs here. Because we're going to go the other way in a minute. Does everybody understand the sig fig rule here for taking logarithms? Yes, 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 yes. Okay, now just a reminder, we are only doing strong acids today. Calculating pH of a strong acid is very different than the way we calculate weak acids. Okay, weak acids are going to involve ice tables. As we'll see today, strong acids are not. Okay, so no ice table today, yes ice table Monday. So a strong acid doesn't need an ice table because these K values are greater than 1, and they're usually significantly greater than 1. I think the Ka for HCl is 36, somewhere in that neighborhood. You can look it up, table online. I'm pretty sure Ka for HCl is 36. I'm pretty sure that's what it is. So that's extremely product favored, right? Extremely product favored. We actually assume that the concentration at equilibrium, if I began with 5 molar HCl, then I'm assuming that the concentration of hydronium is 5 molar as well. Okay? So whatever this number is here, that's the same as the concentration of this and this. Okay? We're assuming 100% dissociation. This is why we don't need an ice table. Does everyone see why we're not going to need to make an ice table here? Because we're assuming it's 100% here, 0% here. Now, when it's a weak acid, it's not going to fully dissociate. It's going to dissociate just some small amount. And we can't say all weak acids dissociate the same, so that's why we have to use an ice table for weak. But for strong, it's 100% dissociated. And remember, back to Wednesday, I gave you a list of those strong acids. Okay, so there are only, I think, what, 7? So your time that you use that is a lot less than the time you're going to be using it for a weak acid. So fully dissociates. So how do I get the pH of a strong acid? I just take the negative log of whatever the acid's concentration is. So if I told you the concentration of HCl was 5 molar, and I wanted to know what's the pH, you just take negative log of 5. Okay? So why don't you try these on your own? Calculate the pH of a 1.15 times 10 to the negative 3rd molar hydrochloric acid solution. Calculate the pH of a 0.31 molar perchloric acid solution. And use this as an opportunity to practice your sig figs too. I'll pause the video. Let's see what we got. So for number 1, we're taking the negative log. We're taking the negative log of both of these. And I can just take the negative log of these values, no ice table, right? Because is hydrobromic acid a strong acid? Yes, it's on my list. Perchloric acid's also on my list. So, negative log of that. Now here, I've got 3 sig figs, so that means I keep 3 decimal places in my pH. Did you get the same number I got? Yes, yes, yes. Again, if your calculator tells you error when you enter that negative in front of log, just take the log and change the sign, okay? Some calculators are okay with that negative. Some calculators make you put parentheses around it, and some calculators just tell you error. So just figure out what you need to do in your calculator. And if you need help with your calculator, I'm happy to look at your calculator for you after class. All right, for number 2, we've got 2 total sig figs. So what's that going to mean in terms of my pH? It needs to have 2 decimal places, right? So 0.51 is what I got. pH is unitless. pH is unitless. Yay! So that's one less thing to worry about. Do we agree on these 2 problems? Is everybody good on how to use your calculator? Any questions involving your calculator? Okay, let's go the other direction. So because a logarithm is base 10, right, log base 10, what is the anti-log? Well, think about when we did natural logs, right? When we did natural logs, we said we raise both sides to the e to get rid of the natural log. To get rid of a logarithm, we'd raise both sides to the 10, okay? So if I've got concentration of H2o plus, if I've got pH and I want to know concentration of hydronium, it's just 10 to the negative pH. Okay, just 10 to the negative pH. So in your calculator, you should have a button, which is a scientific calculator you do, 10 to the x, right? So let's pretend I want to enter 10 to the negative 3.1. On my calculator, I'd say 3.1, change the sign to negative, and then I do second log, and that gives me my number. That's how it is on my calculator. This is the TI-30XA. So if yours is a Texas Instruments, which most of you I think have, you should have a button 10 to the x. It's second log on my calculator. Just like e to the x is second natural log. So let's practice that. pH of a detergent is 10. What's the hydronium ion concentration in this detergent? All right, so hydronium ion is just 10 to the negative pH. So when I enter that in, now I did have a problem here in my sig figs. Wait, no, that's correct. Number of decimal places equals total number of sig figs. So yes, I'm correct in my sig figs. I keep 1 sig fig here because I had 1 decimal place there. Now hydronium ion does need units because it's a concentration, right? pH is unitless. No units needed for pH. But hydronium ion, remember those brackets, what do those brackets mean? It means moles per liter, right? So you need concentration for a hydronium ion concentration. So you try this one. pH of blood under normal circumstances, so no ketoacidosis going on or anything like that. pH is approximately 7.4. What is the hydronium ion concentration under these conditions? Give you a second to try that. Okay, let's see what we got. In terms of sig figs, what's the rule? If I've got a pH, I look at the number of decimal places, and that becomes the number of total sig figs in my concentration, right? So there's 1 decimal place here, which means 1 total sig fig here. And again, don't forget units, because this is a concentration. Those brackets mean molar concentration, right? So I need units. So either put your capital M, or if you prefer, you can just write out moles per liter. That's fine too. I'm happy either way. As long as you give me the unit, I don't care if you write capital M or if you write out moles per liter. Makes no difference to me. Questions on this one? Feeling okay? Everybody good on using your calculator? Everyone able to enter it correctly? Okay, now anytime you see P in front of something, you should automatically think, okay, negative log. P means negative log. So that means POH would be the negative log of hydroxide ion. pKw would be the negative log of Kw. This is something you'll see a lot in organic chemistry. pKa will be the negative log of your Ka. Okay, so anytime you see a little p in front of something, that just means take the negative log of whatever it is. Okay, so pKa would be the negative log of the Ka. POH would be the negative log of the hydroxide ion concentration. Anytime you see that little p, just think negative log. Okay, that's where pH comes from, that's where POH comes from, which is what we're going to talk about today as well. And we'll talk about pKa's next week. And you'll see this a ton in organic, a ton. So POH, like I just said, is the negative log of the hydroxide ion concentration. And so, again, bases that are strong fully dissociate, right? We're not going to need an ice table to figure out concentrations for a base because it's fully dissociating, right? So at equilibrium, if my initial concentration was 5, then I'm assuming that this concentration and this one are also 5. When we talk about weak bases, guess what? We're going to use an ice table, okay? So what do I do to get the POH? Just take the negative log of whatever the base concentration was. So let's do this one together. What is the POH of a 0.111 molar NaOH solution? Is sodium hydroxide a strong base? There are only 3 strong bases. Sodium hydroxide one of them? Yeah, it is. So all I need to do is what? Take the negative log of 0.111. Now in terms of sig figs, these 3 decimal places mean what? 3 total sig figs. Good. So when I take the negative log, my final answer has 3 sig figs. This 0, just a reminder, is not significant, right? Because it's a placeholder. Don't forget that this 0 right here is not significant. POH, just like pH, is unitless. So why don't you try this one? What's the POH of a 9.5 times 10 to the negative 3rd lithium hydroxide solution? And use this as a chance to practice sig figs just to make sure you understand the rule. But we got, what did we come up with? 2 total sig figs, right? So 2 decimal places. pH is unitless. Do we agree? Did you get the same answer? Any questions on how to do this? Now, the way I undo a POH is the same way that I undo a pH, right? If I want to get the hydroxide ion concentration, if I know POH, it would just be 10 to the negative POH. And then my sig fig rules that we just discussed with hydronium ion are going to work exactly the same as those sig fig rules here. So for instance, if I said, okay, the POH of an NaOH solution is 5.44, how much hydroxide ion is in there? And I want it in concentration, so I want moles per liter. Right, so that would just be 10 to the negative POH. So that's just 10 to the negative 5.44. So in my calculator, I would say 5.44, I change the sign first, second log, that gives me 3.631 times 10 to the negative 6th. I can only keep 2 total sig figs, right, because I had 2 decimal places here. 2 decimal places here means 2 total sig figs here. And again, because this is a concentration, it's a molar concentration, I need to either write capital M or write out moles per liter, okay? Whichever way you want to do it makes no difference to me as long as it's either capital M or writing out moles per liter. So you try this one just for practice, practice with sig figs, practice with using your calculator. Here's the POH, it's 3.41. I want to know what's the hydroxide ion concentration. Okay, let's go over this problem. Did you get 3.9 times 10 to the negative 4th moles per liter? Do we agree? Yes. Any questions on calculating hydroxide ion given POH? Is everybody good? Now here's a fun little derivation I'm just going to show you so that you can have an idea of where it comes from. Here's Kw, right? That's where we started today. And I told you, okay, this is great. It's going to lead us into pH. How's it going to lead us into pH? So this is the value at what temperature? 25 degrees Celsius, right? So if we took the log of everybody, took the negative log, I should say, what's the negative log of that? What's the definition of negative log of H3O plus? pH, right? And then remember your log rules when you're multiplying logs. This is you can do this rule where you're adding them, right? So this is pH, this is pOH, and then what's the negative log of Kw? We call that the pKw. If the value here is 1 times 10 to the negative 14th, that's just taking the negative log of 1 times 10 to the negative 14th, which is what? 14, right? We get this nice little tool. This is really convenient. This will allow me to turn my pH into a pOH or my pOH into a pH very conveniently, right? So this is a rule that you can use where you can turn a pH into a pOH or a pOH into a pH very easily just by subtracting from 14. Okay, keep those 2 decimal places there though. Just remember that. So now if I know pH, I can find pOH nice and easy. Is everybody good on this relationship? I'm not going to make you derive it, but I like you to see where it comes from. All right, so there are 2 relationships that are meaningful. This is what we started with at the beginning of class, right? This is Kw. So if I have hydronium and I have hydroxide, I can multiply them together and I can get Kw. So if I know hydronium and I want to know hydroxide, and I know that I'm at 25 degrees Celsius, I can just do what we did at the beginning of class. Or what I just did, taking the negative log of everybody, get this version of it. pH plus pOH equals 14. So these are nice, significant relationships that I can use to convert hydroxide into hydronium or pOH into pH, and vice versa. So this is a summary of all our formulas that we've learned today. These are all our formulas that we've learned. And so let's do this one together. If I know pH, I can solve for all the other variables. If I know this one variable, I can solve for these other 3. And it's not going to be too nasty of a calculation either. Again, this is a strong acid. We're assuming this is all strong acid. So the pH is 7.41, so that's pretty close to neutral. Right? I want to know pOH, hydronium ion concentration, and hydroxide ion concentration. So you can solve these in whatever order you want. The first thing that I would do is solve for pOH. That's what I would do. And so I just subtract it from 14. Right? There's my pOH. Now, how can I get H3O plus and OH minus? How can I get H3O plus? What could I use to get H3O plus? If I know pH, is that enough information to get hydronium ion concentration? Yeah. How do I get hydronium ion? 10 to the negative pH, right? And now once I know H3O plus, I can use the Kw expression. That would work. Or what's the other way I could get pOH? OH minus concentration. I want this, so I could plug into the Kw expression. That's one way to do it. What's the other way I could get this? Do I know the pOH? Yes. And so how do I get hydroxide ion concentration from a pOH? It's just 10 to the negative pOH, right? And don't forget, these are concentrations, so they need units. pH and pOH do not. How do we feel about this one? So I could give you any one of these variables, and you could solve for the other 3 from those relationships. How do we feel about this? You're going to practice it, so if you're feeling a little funny, it'll give you a chance to practice. Okay, why don't you try this one? The hydronium ion concentration at 25 degrees Celsius is 2.1 times 10 to the negative 7th moles per liter. I want to know pH, pOH, and hydroxide ion concentration. I'll pause it and let you try this one. Don't forget Sig Figs. See what we got. So first thing I did is I converted it to pH. So just FYI, some textbooks still write H2o plus as H plus. It drives me bananas when I see a textbook that does this. So every now and then I'll throw one of these in as H plus just so you see it, okay? Some textbooks still write H2o plus as H plus, okay? Which is not correct. So just FYI, if you're looking at something online or you're looking at a different textbook and you see H plus, just remember that person messed up, right? It should be written as H2o plus, just FYI. So I took the negative log to get pH, then I subtracted from 14 to get POH, and then I said 10 to the negative POH gave me concentration. Do we agree on our values and number of sig figs and units? Any questions on where these numbers came from? How do we feel about this? Thumbs up? Yes? All right. Why don't you try another one? pH of a fertilizer is 8.94. So based on that information, what are the other values? All right, let's go over this problem, see if we agree. So what I did, and you can do this in any order you want, right? I calculated hydronium ion concentration, and then I calculated POH, and then I calculated hydroxide ion concentration. You should have the same numbers regardless of the order that you do it. And following our sig fig rules, do we agree on values, sig figs, units, etc.? Any questions on how to do this? Pretty straightforward, I think. Yes? Yes, yes, yes. Everybody good on your calculator? How to enter it in your calculator? Everybody good on that? Okay. Now, if you notice something, here's something fun, right? The pH scale and the POH scale are opposites of each other. So in other words, if you're an acid, you'd have a pH of 0 to 7 on the pH scale. But if you're an acid on the POH scale, you have a POH of 14 to 7. Right? They run opposite each other. And again, it's log base 10, so that means there's a 10-fold difference between each value that you see on both the pH scale and the POH scale. The last thing I want to talk about is pH meter, which we'll be using in lab. Okay, so the pH meter, how does it work? Well, acids and bases are electrolytes, meaning they conduct electricity. So when you're using a pH meter, you're actually measuring the voltage of your solution. That's what you're measuring. And then the device then converts that into a pH for you. So your output is a pH. You don't have to do anything to it. But what's being measured here is the voltage, actually. So that's how the pH meter works. And then chemical indicators. So these are substances that we add. They're usually weak acids, weak bases. We add to our solution, and then it'll turn a different color when it's acidic solution versus a basic solution. So phenolphthalein is one that you may have seen in high school. It's bright, bright fuchsia in basic solution, and it's colorless in acidic solution. So you can pick the indicator that you want to use based on the pH range that you're going to be titrating. So that's a chemical indicator. Do you need to do a review problem, or do you feel like you're good on this kind of calculation? Do you want me to pause it and let you try it, or do you feel like you're okay? I'll just show the answer. That way, if you want to watch it later, here are the answers. Right? If OH minus is what I'm looking for, I know H2O plus, and then is this acidic or basic? So I could use the KW expression. That'd be the most straightforward way to do this. I mean, I could convert it into a pH, subtract, and get a POH. But the easier way to do it, since I just know this one value, is use KW and then look to see which value is bigger. That's what I would do. And then here's another one, like what we were doing a few minutes ago. Here's pH. What are all the other values? Do you want me to pause it and let you try it, or do you feel pretty good on this? I'll put the answer on there. That way, if you want to go back and watch it later. Calculate the pH. Calculate POH. Then you get your two concentrations. And then this one, let's just talk about verbally. What is the difference between a strong acid and a weak acid? Because if you don't know this, how to do the calculations is kind of irrelevant. Because this is how you decide which calculations to do. What are the differences between strong acids and weak acids in terms of their Kas? Strong acid has Ka greater than 1. Weak acid has Ka less than 1. For our calculations with strong acids, do we need ice table? No. Whatever the acids calculation is, that's what we just take the negative log, we're off to the races, right? Weak acid, we're going to have to do an ice table, right? Because they do not fully dissociate, which is what I just said. All right, so I'm going to stop here so I have time to talk about the test.